welcome back to the third lesson of Unit 5. We are going to be looking at the functions, okay, what a function is. And we're going to be looking at the domain and range or writing down the domain and range using set and interval notation. Okay, so here's the warm-up question. This is basically what we did last time. Okay, I will give you time to finish the first page and I'll just quickly show you the answer in a bit, okay? Okay, so here are the answers. Please make sure you did it right. Again, the mapping diagram, the bubbles, the one on the left should be your input, right? Input in this case is the mode of transportation. Let me write it down here. Transportation. And the second bubble is the y value, which is the output, and that is the number of wheels. Okay. So there's my graph. Again, make sure you label the x. What does x-axis represent and what does y-axis represent? Okay. The domain and range. Recall, domain is just a set of the x values. In this case, they are the mode of transportation, and range is just the output, right? The set of outputs. So all of them, 1, 2, 3, 4. Okay, so that's the first example. Second example here is as determine whether these are linear relations. Recall, well, the ones that are not, recall because this has a variable in the denominator. In that case, it's not linear. Part D, the exponent cannot be not a whole number, right? X is a variable, so it could be anything really, then therefore that one is not. And, oh, sorry, I said that wrong. I was thinking about polynomials. Linear relations, okay, has to have 1 as the exponent. Again, this is x. X could be anything. Okay, it could be 2, could be 3, could be 4, could be negatives, in fact. This is not a 1, so it's not. Again, this one has an exponent of 1, but it exists or it appears in the denominator, which is not okay. This one appears in the numerator, it's fine. Okay, so that's not a problem. This one too, right? That's not a denominator, so that is fine. Okay, so we are going to be looking at the functions today. Okay, we're looking at the functions. Here it says definition of a function. It's a special case of a relation. Okay, so let me get that straight. A function is also a relation. Okay, but it's a special case of relation. Okay, so a function is a relation. However, a relation might not be a function. Okay, so there could be other types of relations that are not function. But a function, if it's a function, then it's a relation, okay? So what's a function? Well, it says for each input, okay, so for one set, remember, relation is how two sets are related, right? We have the input and the output. So a function is a special case. What's special about it? Well, it means for each input, it only produces one output. Okay, so from one set of value, it only relates to one element in the second set. Okay, so let's take a look at the example here. We have two relations here. Relation A, okay, both are the relations, right? And we want to see if any of them is a function. It says which of the above relations is a function. Okay, so if you look at relation A, these are the inputs, right? 2, 3, 4, 5, 6. And they do produce one output each, right? You can see that 5 goes to 12 only, 6 goes to 15 only, 4 goes to 8 only, 3 goes to 9 only, and 2 goes to 8 only. Okay, so each input, it produces one output. Okay, therefore relation A is a function. A is a function. However, if you look at relation B, one single input of 1 actually produces two outputs, namely -1 and 1. So is 4, right? The input of 4, the x value of 4, relates to two elements in the second set, namely -2 and 2. And therefore, relation B is not a function because it fails to satisfy this condition. For each input, it only produces one output, okay? So how can you tell if a mapping diagram is a relation or not? Well, you just need to look at the arrows, right? If there's more than one arrow attached to the input, then it's not a function, okay? if there is more than one input, if there is more than one arrow attached to the input, to one of the inputs, right? To one of the inputs, then it's not a function. And it's not a function. Okay, I usually just write fxn for function. Okay, so here it says write the above relations as a set of coordinate pairs and explain how to determine the set represents a function or just a relation. Okay, so for relation A, we can write it as a set. It's going to be 2, 8, 3, 9, 4, 8, 5, 12, and 6, 15. So this is relation A. For B, we have 1, negative 1, 1, positive 1, 4, negative 2, 4, 2, and finally 9, negative 3. Okay, so B is not a function because we said that there is more than one arrow attached to the input. Now, from looking at the order pairs or the coordinate pairs, you can see that for each input here, 1 and 1, it produces two outputs, right? For that input, it produces two outputs, two different outputs, and therefore that is not a function. So that's how you tell, okay? So if you just look at the inputs, they should all be different, otherwise it's not going to be a function. Okay, so here are 3 examples. Okay, I'll let you think about it and tell me which one is a function and which one is not a function. Okay, hopefully you got this one as the function, right? You can see negative 4, 0, 2, 7, 8, 10. They're all different. Okay, so we're good. Part B, negative 5, negative 2, 0, 3, 5, and 7. Okay, so here's 5, here's 5. Oh, well, that's negative 5. Never mind. So then this one is also a function, right? They're all different inputs. You could have the same output. Okay, that's not a problem. You can see here there's the 2. There's also 2. You can have same output. Sorry, same y values. That's fine. As long as the inputs are different, then it's fine. Here's negative 1. Here's negative 1. Okay, and the outputs are indeed different. Therefore, this is not a function. Okay, that's not a function. Okay, both A and B are functions, but not part C. Okay, because for part A and B, there is only one input for one output. However, for part C, you have one input of negative 1, it produces 2 different outputs. Therefore, it's not a function. Okay, so that's how you tell whether it's a function or not from coordinate pairs. Okay, what about from the graph? Okay, how can you tell whether a graph produces a function or not, or a graph is a function or not? Well, you can see, I mean, you have all the coordinate pairs here written down for you, right? So, I mean, you can tell from there, but it does not always write down the coordinate pairs are not always written down for us, right? Sometimes it's just like a graph, something like that, right? And how do I know if it's a function or not? So here comes the vertical line test. On a graph, to tell whether the graph is a function or not, what you have to do is you can draw vertical lines. Okay, obviously you are not really drawing them. Okay, draw vertical lines. Now, what do we do with the vertical lines? So, as long as, okay, so how should I say this? If there is a vertical line anywhere on the graph, okay, the vertical line anywhere on the graph, on the grid, that crosses the graph more than once, then it's not a function. Okay, So you can draw as many vertical as you want, okay, as long as there is one, okay, all you need is just one. As long as there's one vertical line that crosses the graph more than once, then it's not a function, okay? So you can see here, if we draw vertical lines, it only cross once, okay, you can see the vertical line cross the graph twice, therefore not a function. Okay, we can look at part B, graph B. Here's the vertical line, only once, and only once, right? So therefore this is a function. Okay, this is a function. Okay, because none of the vertical lines that we draw will cross the graph more than once. Okay, it could be twice, it could be 3 times, it doesn't matter, as long as it's more than once, okay? As long as it's more than once, then it's not a function. Okay, so there are 3 graphs here for you to think. The third one might be a little tricky, but give it a try. Okay, part A clearly is not a function. You can see if I draw a vertical line down there, it goes through the graph twice. So not a function. Part B, yes, it's a function. Yes, is a function because none of the vertical line is going to cross across the graph twice or more. Okay, more than once. Every single vertical line is going to only cross the graph once. Okay. Part C is a little tricky. Okay, so you can see in this graph there are like empty hollow holes, right? Hollow dots, and then there's the solid dots, right? So these are the solid dots, and then we have the hollow dots. Now, if you draw a vertical line, well, that's fine. That's fine. Really, the only points that have issues or could have issues would be at the point where we draw the vertical line. It has a solid dot and a hollow dot. Okay. Now, what it means to have hollow dots means it actually does not include that point, right? It's reaching that point, it's getting closer to that point, but it's never that point. So in this case, we do not violate the vertical line rule, okay? So this is actually a function. This is a function. Because this vertical line actually only crossed the graph right there at that point. It does not cross the graph at that point because there's no point there. Right? There is no point there. Okay, so this one is a little tricky. This is what we call the step function. Looks like steps. That's why we call it step function. But this is, well, as you can hear, right? Step function. It's a function. Okay, so that's what a function is. That's how you determine whether a graph or a table. Actually, we didn't look at table, right? But table is similar to the mapping diagram or similar to coordinate pairs. That's how you can tell whether it's a function or not. Okay. The last thing we need to do is to actually write down the domain and range using interval notation and set notation. Okay. So we did a little bit of these last lesson. Actually, during the warm-up as well, right? We did write down the domain and range. Where is it? Right here. Now, notice how these domain and range, they are particular values or particular objects, right? Like unicycle, bicycle, tricycle, motorbike, and the range here is 1, 2, 3, 4. They are what we call discrete data, right? It's just one snapshot, right? One snapshot, 1, 2, 3, 4. Not 1.5. Unicycle, right? Bicycle, that's one object, another object, right? They are discrete data. But we sometimes will run into non-discrete data. We could have continuous data, okay? So that means, like time. You can't just say the time is 1 second, 2 seconds, 3 seconds. What about 1.35721722301 seconds? That's a valid, snapshot of a time. So that is what we call the continuous data, okay? Now, to write domain and range for those kind of situation, well, then we will it says here, let's review inequalities first, okay? So to read inequalities, okay, we always start from the variable, okay? So here are 5 examples. It says graph the following inequality, and actually there's an equality on the number line. Okay, part A, x equal to 3. So that's just 1 point. So then what you have to do is just draw a dot, and that's it. X is greater than or equal to 3. Okay, so again, this means x, reading from the variable x, is greater than, right? The mouth is opening towards x, so it's x is greater than or equal to 3. So here is 3. There is equal sign, so you must have a solid dot. Right here it says it's a solid dot, means included, okay? And it's greater than 3, so it's to the right. So how I usually show this is I draw arrows to the right. Okay, then you can see clearly we're going towards right because it's bigger than or equal to 3. Okay, how is part B and part C different? Well, part C says it's just greater than 3. There's no equal sign. So this case, we need to draw the hollow circle, right? Hollow dot. And then same thing, it's greater than 3, so it's to the right. Okay. Part D, okay, a little trick here. Now we have two numbers. Again, reading from the variable, okay, so from here, if you read this way, it says x is greater than or equal to -1. So at -1, I'm going to put a solid dot, okay, because there's equal sign, right? There is the equal sign there. Now it's to the right of -1 because it says its x is greater than that. So I'm going to draw this way. I'm not going to draw the arrowhead just yet because here it also says x is less than 4. No equal sign, okay, no equal sign, so it's going to be a hollow dot. Oops, I missed it. Somewhere here. And therefore x is between -1 and 4, but not including -1, but not including 4. So you look something like that. Okay. And finally, the last example I need to show you here, it says x is less than -2. So here's -2, it's less than, no equal sign, so just hollow dot. It's less than, so it's to the left. This time I'm going to draw arrows because the other one says x is greater than or equal to 1. And if it's greater than or equal to 1, then it's going to the right. And therefore you don't connect the dots, right? Like in part D, because that's in between. Whereas part E, it's going in the opposite direction. So you need arrowheads for those. Okay, but not for D, because D is just between -1 and 4, including -1, but not 4. Okay, so that's how you draw number lines. Okay, so let's see. How does this help us? Okay, how does this help us? Let's see. We are looking at the domain and range of the following graph using set notation and interval notation. Okay, so set notation first. Set notation is basically what we did earlier. We're going to write down the set. Okay, so set, well, there you go. There's the set symbol, right? Here it says used for set. Okay, now domain, thinking about x values, right? Input, x values. So when we think about the x values, we're looking at horizontal directions, I suppose, right? You're looking from smallest to the biggest, okay? So that's how you look for domain. Always smallest to the biggest. And for domain, because we're dealing with x values, so smallest value will be on the left of the graph, and the biggest value will be on the right of the graph. So if you look at this graph, the point that is on the left the most is this point. The point that is on the right the most will be this point. So the domain would be the x values such that, okay, x is in between, okay, so the x value of this point here is -6, and the x value of that point is actually 7. Okay, so x is between -6 and 7. Okay, however, if you look at the endpoints, right, namely these 2 points, you can see that's a hollow dot, which means does not include. This is a solid dot, which means it includes 7, and therefore we must include the equal sign there. So the domain will be the x values such that x is in between -6 and 7, not including -6, but including 7. Okay, so that's how you write the domain, the set notation for domain. Range is about y values, okay? So similarly, we also think about smallest to the biggest, okay? So to find the domain and range, you always look for the smallest to the biggest. However, domain was looking for the x values. That's why we go from left to right. Range is about y values. So we're going to look from the lowest, which is going to be the lowest point of the graph, okay? So that's this point still, and the highest point of the graph, right? Which is actually still this point. okay? It's still the same 2 points. In this case, not always, okay? But you're looking from the lowest to the highest. Okay, so the range would be the y value such that, okay, the lowest point is this one, which has a value, the y value of -4. The highest point of the graph is that one, and this has the y value of 7. So y is going to be in between -4 and 7. And again, because because we have two different dots, this one is included, and therefore we must include the equal sign for the -4, because -4 is being included. 7 is not being included though, because it's the hollow dot. Okay, so there we go. That's the set notation for domain and range. Okay, okay, this is not supposed to be here. This is supposed to be on the right. That's okay. Interval notation. So interval notation is a little bit easier because, well, I think it's easier. Okay, but yeah, I mean, either way is fine. Okay, it's less writing for sure. Okay, for interval notation, we're gonna use brackets, and there are two kinds of brackets. One is this kind, and one is this kind. Okay, the square bracket means the endpoint is included. The round bracket means, well, it's not included. Okay, and you are gonna use this infinity symbol. Okay, this actually, okay, I mean, I should probably include x is the element of all real numbers here, and here y is the element of real numbers. Okay, recall real numbers are just any numbers that we learned so far, including fractions, decimals, and radicals, and so on. To be honest, I'm not too worried about this, but I think most people do include them, so I'll do the same as well. Okay. Okay, so interval notation, sorry, I forgot about that. Interval notations, again, what you have to do is left to right, okay? So for domain, again, x values, therefore left to right, okay? So domain is going to go from smallest x is -6, the largest x value is 7. Now, -6 is not included, so what you have to do is you need to use the round bracket. 7, however, is included, and therefore you use the square bracket. And that's it. That's all you have to do. Okay, you can see it's much, much shorter, but there are two different brackets, so you gotta keep in mind which one is which, okay? Whereas range, same thing, right? Smallest to the biggest. But for range, you're looking from the lowest to the highest. So in this case, the lowest is -4 to the highest point, which is 7, right? So again, you see, we start from lowest, highest, smallest x value, largest x value, okay? Always smallest to the biggest. In this case, though, -4 is included and 7 is not included. Okay, now there's the infinity here. There's no endpoint, so I will show you an example of that on the next page. Okay, so you know what to do and when we use it. Okay, so here there are 9 examples here. Let me show you the first one here. Okay, so you can see here this graph is as determine the domain and range using both set and interval notations. Okay, and state whether this relation is a function. So first of all, let's look at this graph. Is this a function? Yes, it is. Okay, because no matter how you draw the vertical lines, it's just gonna cross the graph once. So function. Okay, now let me do the set notation first. This one is a set of x values such that x is the element of all real numbers, and that's it. Okay, because it keeps going to the arrowhead suggests that the graph keeps going to the left. There's no end, there's no smallest x value, and the graph keeps going to the right, and there's no biggest x value, and therefore x could just be anything. Okay, so x is the element of all real numbers. Okay, so this backward E stands for the element. Okay, so x is the element of the set real numbers. So this is the domain. Whereas the range, similarly, actually, because the arrowhead suggests that it keeps going downwards, the arrowhead here suggests that it keeps going upwards. So the range is just going to be the y value such that y is the element of all real numbers, because it just keeps on going forever. Okay, now the interval notation. Okay, domain. Now, this is where the infinity symbol comes in because it keeps going to the left, keeps going to the right. There is no end, right? Here it says when there is no end point, then you use the infinity. Now, to the left, though, it's very negative. So we call that the negative infinity, okay? So this symbol is infinity. It means there's no ending. To the positive infinity, okay? So from negative infinity to the positive infinity because it just keeps going to the left, keeps going to the right, and there's no ending. Now, you might ask, well, if there's no ending, then what kind of brackets are we using? Well, if it's not ending, then we cannot include it, and therefore we use round brackets. Okay, for the range, similar, right? It keeps going down, keeps going up. There's no ending to it. So the range is going to be from negative infinity to positive infinity. Okay, let me show you two more, and then I'll let you try the rest. Okay. This is also a function, right? You can see that no matter how you draw vertical lines, they will all just go through the graph once. Okay, so I will do the set notation first. Now there are no numbers here, so let me make some numbers up here. Let me just draw 1, 2, 3 like that. Okay, I think that's all we need. Okay, the domain, you can see the arrowhead suggests that it keeps going to the left, it keeps going to the right. So the domain is just going to be the x values such that x is the element of all real numbers. Okay, whereas the range, we are going to have some limitation here. Okay, so you can see these two arrowheads again tells us it keeps going up, but it does not tell us to keep going down, right? There is a smallest y value, and the smallest y value is right here. This is the smallest y value, and because I gave you the grid here, it is -3, okay? So range will be the y values such that y is greater than or equal to -3, and that y is the element of all real numbers. Okay, so as long as it's bigger than or equal to -3, we are taking all the y values after that, okay? So there you go, part B. And if you want to write this in an interval notation, okay, again, this tells us it's from -infinity to positive infinity, and because it keeps going to the left, keeps going to the right. Range here, though, we do have a smallest y value of -3, so we have to have that. That's the smallest, but there is no biggest because it keeps going up, so that's infinity. And we do not, never, right? We never include infinity, but -3 in this case is included. Okay, so you can see sometimes we end up with this situation, right, where the brackets are two different ones. Okay, I guess I need to again give you some labeling here. I think that's all we need. Okay, this is a function. Okay, again, no matter how you draw vertical lines, it will only go through the graph once. Okay, domain to the left, to the right. So in this case, there's no ending, so x is just the element of all real numbers. However, for the range, there is a restriction, right? We have a highest point right here at 2. It keeps going downwards though, so we don't have a minimum, but we do have a maximum, and the maximum is 2. So we're gonna write y values such that y is less than or equal to 2, and y is the element of all real numbers. Okay, y is less than or equal to 2, right? Because that is the biggest y value. Nothing is bigger than that, but we do have a bunch of values that's smaller than that. Okay, interval notation, same thing. For domain should be from -infinity to positive infinity. Okay, for range, this one should be, we don't have a smallest y value, so that's -infinity. We do have a largest y value of +2. That should be included. Infinity will never be included. Okay, so these are the 3 examples I'm going to show you. There are 6 for you to try. Good luck. Okay, so I just want to talk about, here are the answers. I just want to talk about part E. You can see, notice how I said in the range, we cannot do interval notation for range because it's not an interval, right? You can see for y values, they are just some numbers, -3, -1, 1, and the 3. It's not an interval, and therefore we cannot write down interval notation for that range. Okay, so these are the answers for D, E, F. Okay, here are the answers for G, F, G, F, G. What the? D, E, F, G, H, G, E, F, G, F, G? What? Okay, anyways, the last three. Again, notice how for part G, or the second part G, with two G's, for this one here, it's a function, but you cannot write down interval notations for the domain and range because you can see they are just particular points, right? 3 points. They are not intervals. So there's no way you can write interval notations for those to write a domain and range because they are just particular points. So you just write down what the numbers are, okay? And that's it. Okay, this usually is quite challenging for students to get a hang of it. Okay, so make sure you do lots of practice for the figuring out domain and range, and let me know if you need some help. Okay, good luck.